atomic structure and how the scientists were able to explore the atomic structure and get to know the details of the atom. In the last video, we saw how they were able to understand the electrons and the presence of electrons and the charge of electrons using the cathode ray tube and the Millikan experiment. And now we will go to the other part of the atom, which is the positive part. So the scientists were kind of have an idea that there is something positive in the atom, and this positive particle should be there because the atom is electrically neutral. So there must be something that neutralizes the negative charge in the electrons. And this was kind of not totally understood until the experiment was done with the cathode ray tube using by a scientist whose name was Goldstein. So Goldstein did a very, very smart modification to the cathode ray tube, which is using instead of having a normal cathode in the setup, he used a perforated cathode. So it's like something like what we see here in this photo. So it's a cathode that has some holes, and in this schematic we'll see that when the voltage is turned on, the electrons will migrate from or will be kicked out of the electrons of the atoms and migrate to the positive anode. And here we'll have the positive ions, which are the ions after losing the electrons. So these positive ions would go to the other way. They repel with this positive pole and will go to the other side through the holes in the cathode. And and this is what we will see when the experiment was done, that there is this rays that we see, which are the cathode rays, which was the same color that we saw before. But here we will see the anode rays, and these are the rays that are emitted due to the migration of the positive ions to the other side of the cathode ray tube. So and by seeing this, we now have an evidence that there is something positive in the electron, in the atom, and that these positive particles neutralize the atom. So the atom is electrically neutral. The experiment was done with many atoms, and there were some experiments that were done to measure the weight of these particles, and it's kind of similar to the experiments that were done to the electrons to calculate the weight and the charge of the electrons. And they will find that the charge was the same, but it's positive and the other was negative. And here they were, in this case, there was a difference, that the positive particles that were got are different in mass from one gas to the other. So in the previous case, we said that the electrons were always equal in mass, but here the positive particle in the atom was different. And of course we now understand that this is because the protons in the atom are different from the protons of the atom of another element. But the smallest positive particle was got when the experiment was done with hydrogen, and these particles were called the protons at this time. And they were the charge to mass ratio was found to be with this number, so it should be coulomb per kilogram. This is a mistake. And this was the first time to understand that there is a positive particle in the atom. And then the first atomic theory or atomic model was made by J.J. Thomson. And he called this the Plum pudding model. So this model assumes that the proton is kind of big lump in the atom, and that the electrons are embedded into this positive particle. So this is what we see here. So he called it the plum pudding because the plum pudding is kind of something like this. It's kind of cookie that has or a cake that has raisins in it, and the electrons resemble the raisins, and the proton or the positive particle resembles the cake itself. So this was the very first model that was made for the atom. And of course, this was a very reasonable model according to the inputs that they had at this time. This is what they did. In kind of few years after this, this very great scientist whose name was Röntgen, he did some experiments with the cathode ray tube, and he noticed that there are some crystals that were present near the cathode ray tube, and these crystals started to glow when the experiment was done, and he did some shields between the cathode ray tube and the crystals, and still the crystals were glowing. So he was able to conclude that there are some radiations that come from the cathode ray tube, and that these radiations can cause this glowing. So his experiments showed that these rays can blacken the photographic film. So if you have a photographic film, it will cause kind of change in the color of the photographic film. They ionized gases, and they were able to make gases able to conduct electricity, and they made some materials like zinc sulfide to make them fluorescent, and they are not charged. These radiations were exposed to electric and magnetic fields, and nothing happened to them, so it's not charged. He didn't know anything about this rays, so he called them X-ray, X for the unknown, the variable that he's not familiar with. So he called it the X-rays, and in after a few years, it was shown that the X-rays are just radiations. They are not particles, just like light. But light has a smaller wavelength, so this X-ray has higher wavelength, so it has higher energy, and this energy makes it able to penetrate and do all these kind of things. And this guy was able to use the X-rays to show the bones in the body. So his experiments showed that the X-rays were able to or can penetrate the muscles, the skin, but cannot penetrate the bones. So this is the very first photo that or X-ray radiograph that was ever made, and this was Röntgen's wife, and he did the X-ray on her hand. Of course, in this time they didn't know that it's dangerous to get exposed to X-rays a lot, and for instance, one time this Röntgen was giving a talk, and during the talk he did the X-ray experiment to the hand of one of the guests in this talk, and everybody was looking at this, and no precautions were taken. Of course, now when anybody does the X-ray on his hand or foot or something like this, you have to wear lead shield to make sure that the radiations will not harm your body. Anyway, so this was kind of very important exploration at that time. In the same kind of period of time, the very famous scientists Pierre and Marie Curie, they did experiments on radioactive materials, and they explored materials like uranium, polonium, and radium. And by the way, polonium was this is the material or the element that they explored themselves, and they named it polonium because they were from Poland, and they called it according to the name of Poland. So they were kind of very like they love their country very much, that they call the element like their country's name, and they accept or found that the materials, the radioactive materials, emit some different types of radiations or particles, and the experiments that were done by Rutherford and another scientist whose name was Becquerel, they found that there are different particles like alpha particles, beta particles, and gamma rays. The alpha particles were found to be positively charged particles, and this is the reason I'm talking about these actually now, because we're going to talk about alpha particles, and alpha particles are kind of very important breakthrough in this field of science, and it was used a lot to explore the components of the atom. So the alpha particles were found to be positively charged particles, and found that it's helium with losing two after losing two electrons. Beta particles were just electrons, negatively charged particles. They have different speeds, and some of them were very had very high speeds, maybe close to the speed of light. Gamma rays were found to be just radiations like X-ray, but they had even shorter wavelength and higher frequency, so they're even more powerful type of radiations. The alpha rays were used in many experiments, and the most famous experiment of them was done by two scientists, two very famous scientists whose names are Hans Geiger and Ernest Marsden. Geiger is very famous because the device that used to measure the radiations of radioactive materials is named after his name. It's called the Geiger Counter. They did experiments to understand the nature of the atom, and to kind of confirm the Plum pudding model that was done by Thomson before. So they did a very smart experiment. Actually, they used the gold foil. It's very thin film of gold. It should be like very small thickness, so you don't have a lot of layers of atoms in this foil. And they had this zinc sulfide screen that was kind of surrounding the gold foil, and they had this lead block. Of course, they used lead because lead prevents radiations from penetration, or does not allow penetration of radiations. So they had this block with a small hole, and they had the radioactive material that produces the alpha particles. So the using this setup, you would only get a beam of alpha particles that's going in this direction, and it should penetrate the gold foil. According to the model that was done before, which is the Plum pudding model, we should have big particles, which is the atoms, and they are kind of stacked together. So you shouldn't expect a lot of penetration if this model is right, and you would get more and more reflection like going this way than the penetration or refraction or deflection, I mean. So to their surprise, most of the particles were able to penetrate the gold film, and small portion deflected, and even a smaller portion reflected. And this was kind of very surprising to them, because it's not what they expected, and this was a very important modification to the model, or it kind of destroyed the old model, and they kind of came up with the new shape or model for the atom, which is closer to the actual model that we know today. So the great or the big ratio of particles that penetrated the foil means that there is a lot of space in the atom, and this space allows the particles to go and move through the between the particles and go to the other side. And this kind of led to or after some experiments, led to the conclusion that the atom is composed of the positive particle, which is the protons, and the electrons, and they are not kind of sticking together, as we said before, and that the weight of the proton is the big part of the weight of the atom. It's mostly concentrated in the proton, and that this is the bulk of the weight, and then the whole space is just space. It's not filled with any material that has a contribution in the weight of the atom. And that the reflection and the deflection was because some particles either like hit the nucleus, or reflected over from the nucleus. And this kind of what we call here the electron cloud that surrounds the electron, is where the proton or the electron, or the place where the electrons are kind of rotating. And this was the new model, which is the Rutherford's model of the atom. It didn't tell that there is a specific place where the electrons are rotating. It just said that the electrons are somehow rotating around the proton, and this was now proven to be wrong. Just for one last thing, to give you a feeling of the dimensions of the atoms and the weights and the volumes, it was found that after, or the new results or the new experiments showed that the radius of the atom is from 10 to the minus 14 to the 10 to the minus 15 of a meter, which is very small distance, and this is the nucleus, and that the atom itself is 10 to the minus 10 meter, which is the electron cloud surrounding the nucleus. So this is how the electron cloud looks like, and this is the nucleus, very small inside. You might feel that this is very small and this is very small, so it's not a big deal, and actually it's important to know that this is 100,000 times greater than this. So the nucleus is 5 orders of magnitude smaller than the atom. So I had in this was drawn to scale, by the way. So I have the nucleus is very small, so you cannot see it by your eyes, and I had to zoom this 1,000 times so that you can just see the nucleus, and you have to increase this like 100 or 1,000 times so you can get this in the same side of this electron cloud. And to give you a feeling for with something that you're familiar with, if the nucleus is a grain of sand, then the electron cloud would be a big watermelon. So a watermelon that is 60 centimeter in diameter, so it's kind of something like this, and the nucleus would be just one grain of sand. And this tells us that if you do some calculations, you would know that the volume that is occupied in the atom by the particles, the nucleus and the electrons, is 10 to the minus 12 of that volume. So the rest of the 10 to the minus 12 is totally free. It's empty space. The electrons are just moving around inside the space, and a small part is taken by the nucleus. So this is what we know till now. We are gonna see in the next videos how the scientists were able to know about the neutrons and the atomic number and the other related parts of the atom. So I'll see you then, inshallah. Goodbye.